Yes, now we are going to see universal gates. Our topic is universal gates. Um, as we have already discussed, basic logic gates, combinational logic gates, and exclusive gates also. Now you have got an idea about all the logic gates. Then there is a term called universal. Universal gate is a logic gate. It can be used to construct any basic logic gate. There are two universal gates. You take NAND gate and NOR. These two gates are taken as universal gates. When designing circuits, these two gates are mainly used to create integrated circuits. So, when creating integrated circuits, there are various advantages by using NAND and NOR gates rather than using a basic logic gates. So, what we want to learn here, if we need to get a NOT gate, OR gate, or AND gate in integrated circuits, we can see NAND or NOR gates are used. So today I'm going to discuss how NAND gate or NOR gate is used to create a basic logic gate. Now, what are the basic gates? NOT gate, AND gate, and OR gate. Right. Now, let's see. NAND gate. NAND gate can be used to create NOT gate. Right. There we get a single variable and input this variable from both sides. Same variable from both sides to a NAND gate. You see, this is the NAND gate. Then what may happen? A here and A here. A can be insert from both sides, there should be two input to a NAND gate. So then output can be like this, A and A bar. Now how you can understand? A and A bar is equal to A bar. If you take A and 0 or 1, and again another A as 0 or 1, what may happen? A and A, 0 into 0. A and A means A. 1 into 1, 1. A and A means A. So A and A bar means the opposite of that. So it is equal to A bar. Output of NOT gate. If you input A, you get A bar. Now what has happened here? You have entered A into an AND gate and has taken A bar as the output. So what is this? This is actually NOT gate. Right. I think this is the idea. You may have taken the idea as NOT gate. Right. So here this is NOT gate. You NOT gate using NAND gate. Right. So the first example is NOT gate has created by using NAND gate. Then let's see another example. What is the second one? It should be AND gate. Here, if it is AND gate, we need two variables, A and B. Otherwise, we cannot say. But here, we input A and B to a NAND gate. Then we take our output A and B bar. The first NAND gate. Then as you have entered these two values, you have taken A and B bar. In order to create AND gate, you need another NAND gate. So there the output of first gate is passed to another NAND gate. See, this is the second NAND gate. So the second NAND gate produce A and B again. See, you input A and B and you take the output as A and B bar. Then you input A and B bar from both sides. A and B bar. A and B bar and A and B bar. It means A and B bar. So A and B bar and A and B bar in the sense A and B bar and opposite of A and B bar. So opposite in the sense. See, if you have A and B bar here, what is the opposite? It should be A and B. So then we can remove these two bars. Because A and B bar can be A and B double dash here. Suppose if you have taken 1 as A and B bar, what is the opposite of that? That is 0. But here, if you want to take 1, you should input 0 from both. See? 0 into 0. 0 into 0, 0. Here you take 1. So then 1 into 1 is 1. You take 0. So you can understand A and B bar. If A and B bar is 1, A and B double dash become 0. So first input, this is the input, A and B. So it means we can remove these dashes. It means we have taken A and B again. This is AND gate. By using two NAND gates, we can produce AND gate. So we say AND gate using NAND gate. Right. Is it clear? We have A and B. So we input A and B. Again, we take A and B as the output. A and B bar, opposite of that is A and B. So by connecting two NAND gates together, we can create a new AND gate. This is AND gate. Right. Now try to get an idea. If you have any questions, I will further explain it. So then you can send me a message. Then I will explain the entire idea again. Right. Now we know NAND gate can be used to set up a NOT gate. NAND gate can be used to set up an AND gate. Then what you need? You need the OR gate also. Right. Let's see. If you want to set up what you call OR gate, you need three NAND gates. So in this example, we have to draw 3 NAND gates. Let's see how we can get it. I take one variable called A. Then A can be passed from both sides to a NAND gate. This is the first NAND gate. A. So A is coming from both sides. It can be A and A bar. This is equal to A bar. You need another variable. It's better to take B. B is also input to another NAND gate. This second NAND gate. This time the NAND gate, it produces B from here and B from here, and B and B bar means B bar here. Now output from these two gates are again sent to another NAND gate. Now we have A bar here and B bar from this gate and comes to another NAND gate. Now this gate says this is an AND gate, so A bar and B bar full dash. This is the circuit. But what is the idea of this gate? This gate has developed in order to construct the OR gate. Has it come? Now, what I want to show you, how this output can be taken as OR gate. Our topic is creating OR gate. Creating OR gate using OR gate using NAND gates. We have NAND gates. If you put this one into a truth table, if you get a truth table, you can prove something like this. You can say A bar and B bar full dash is equivalent to AOB. If it is true, you can understand this is the OR gate. In logic gates, there is a theorem. There is a theorem called De Morgan. That is De Morgan theorem. De Morgan theorem, later we will discuss the De Morgan theorem. But remember, De Morgan theorem says if there is a full bar like this, we can break it and we can separate these two terms by dividing the full bar. De Morgan says if there is a full dash in a Boolean expression, you can divide the entire expressions into two parts from the operator here. So the rule is break in the bar and change the operator. So what we are going to do, we break the bar. So then there are two bars. Change the symbol, should be 1. Then under that A double bar and B double bar here. A double bar and B double bar here. Double bar in the sense, if you see double bar in any situation, double bar in the sense we can remove all bars. So what we are going to do, we have A double bar here, O B double bar here. So then we remove. See what may happen after removing, you get A O B. This is De Morgan theorem. Later on I will discuss De Morgan theorem with some truth tables and others. But up to this, remember, if you use 3 NAND gates together, but with a single input, remember, we always, why we want to get AOB, so we always use single input here and take 3 logic gates in order to construct NAND gate. We should familiar with this. So then what we have discussed so far, and we have taken time to discuss how NAND gate is devoted for creating basic logic gates. NOT gate, AND gate, and the last one is here OR gate. The special thing is you get output like this, A bar and B bar full dash. But by using De Morgan theorem, we can break the full dash and you can change the operator. After changing it, you have double complements here. You can remove double complements, then you get AOB. This is OR gate. AOB. Right. So these 3 gates are very important when thinking about the A-level exam, because they may ask you to use such combination in order to produce something like this. So now you need to think about the actually contribution of logic gates for the exam and how many marks can be taken. At least if you are actually doing or selecting the logic gate question in paper 2, 15 marks is given for that question. And even in the first paper there may be 2 or 3 questions. So then around 18 marks for logic gates. Around 20, because there are some different areas actually, half adders, full adders. In the latter part of this unit you may see different things. These are actually related to logic gates, different topics really, but the same unit. So the contribution is so large. Then I think we need more exercises in order to get marks from this unit. But the main thing is understanding this concept and try to draw in and practice. You know, it is better if you can draw these diagrams and get the idea and practice it. So then it will be easy for you to do these questions later. Okay, then we can discuss how actually NO gate can be used to produce basic logic gates. Okay, we will see how we can do it. Right. Now we are moving to NO gate. The second universal gate, NO gate. The first thing is, NO gate can be used to create a NOT gate. So you need one input, and take input as A. Then A can be entered from both sides as this into a NOR gate. This is the nature. A is coming from both sides. The gate is NOR, so it should be A bar AO A bar. AO A bar. So A is the input. AO A bar means A bar. Because A, if A is 1, the next A is also 1. So 1 O 1 in the sense 1, otherwise 0 O 0 in the sense 0. So the same value A. A O A bar means A bar. So it is NOT gate. See that NOT gate. Using NOR gate. NOT gate using NOR gate. Here we have a NOR gate, but actual representation is NOT gate. Right. So you can see the given note actually. You may identify all these things, and again see the video how I draw it and take the idea. This is actually NOT gate, but the main idea is NOR gate. Right. Then we have two more, and one is we need the OR gate and we need AND gate. Now when drawing these, actually constructing these gates, this time we don't go for AND gate, instead we go for OR gate. Why? We need only two NOR gates in order to get the OR gate. So it is easy. Now we get two variables A and B input values. We have a OR gate here. Now put the inverter and take AO B bar. Then this output is passed into, the output can be passed from both sides. We use the same output here, AO B bar, here also AO B bar, into another NOR gate. So this is the second NOR gate. Second NOR gate. What is the outcome? AO B bar or AO B bar means AO B bar and the complement of this AOB double dash. So then you know, if you can see A or B bar here. This is the opposite of A or B bar. So if you input A or B, then you take A or B bar. If you get the opposite of A or B bar, what may happen? You can cut these two, then it will become A or B. This is all it. It is easy. Now you are having two NOR gates. We say O gate using NOR. So here NOT gate using NOR gate. Here we have O gate using NOR gate. This is the idea. So universal gates can be used to actually represent basic Boolean expressions. By using these combinations. So any basic Boolean expression can be created with NAND or NOR gates. But we don't go for drawing these gates here. The reason is this lesson, this part is not easy. So you have to consider more. You should develop your background. Then you can go for exercises. So what I wanted to tell you here, if you try to draw these things and if you get the idea, then you will be able to convert these things. You will be able to apply actually. You will be able to apply these things into different situations. Okay, now what we have done so far, we have discussed two gates, NOT gate and OR gate, by using NOR. NOR is the universal gate here. Then the last one, I need to show you how to produce AND gate, because what we did up to now, we discuss NOT gate and OR gate. We need AND gate here. In order to create AND gate, we need three NOR gates. So we get values. I would like to get A and B. A is used to send input to the first NOR gate. This is the first NOR gate. A is coming from both sides. A, O, A. We have inverter here. A, O, A bar. Now it means A bar. But here we have B. We get B from both sides to the second NOR gate. This is a NOR gate. So we have B, O, B bar. Now you are familiar with this. This B bar. Now we need the third one. Third NOR gate. Here we get the output from both gates and pass into another NOR gate. The third one. Third gate says, now here A bar is coming. Now from here B bar is coming. Now the output is a OR gate. So A bar, O, B bar, full dash. A bar, O, B bar, full dash. Have you remembered the theorem I told you? There is a theorem called De Morgan theorem. Later we will get a note about De Morgan. This is a very important theory in Boolean algebra. We haven't discussed Boolean algebraic rules for simplification yet. So we need to discuss them later. Until this, remember, if you have a situation like this, the De Morgan theorem can be used. How? You have a full bar, and under that you have something like this: A bar or B bar, full dash. What you can do, you can break that dash line and you can change the operator. There are two things to do: break in the bar. The next thing, change in the operator. Change in the operator. We do these things. We break the bar. So bar goes like this. We change the symbol into AND. So under this, A bar and B bar. Then you have double complements. You have double dashes. If there are double dashes, what we can do, we can cut them easily. So we remove. So then A and B remains. A and B remains. What is A and B? This is A and B. So applying De Morgan theorem, we can directly get A and B. Otherwise, we had to go for truth tables to prove in that. I didn't use truth tables. Rather than that, this way is easy because this is the De Morgan theorem. Later, even we will discuss De Morgan, then you will do these things very easily. So with the De Morgan theorems, we can do. Now, what we have learned so far? We have learned NAND gate and NOR gate. They are universal gates. Why we say as universal gates? They are used to create all the basic logic gates. Universal gates are used in IC designs, in integrated circuits designs. So this part is very important. This is a new thing. You haven't done these things at O level, I think. They haven't discussed about integrated circuits and their structures at O level. So we need these things for the level exam. It is easy if you think about the basic idea. By using these gates, what we have done, we have moved back to the basic gates again. Earlier, I think in the first part or the second part, we have discussed the basic gates. Now you know standard structures are used like this. So NAND gate and the NOR gate is mainly used to produce other gates. And when designing these gates, you actually haven't seen such different Boolean laws, but this is easy. Don't worry about this. And you can note down these things also when taking the note and get the idea. Because if you put them in a truth table, what you need in truth table, you need A and B, then A bar and B bar, then A bar O B bar, and again A bar O B bar full dash. So after getting this, the A bar O B bar, that A bar O B bar full dash should be equivalent to A O B. So using a big truth table, you can get the same. But I don't use truth table here. Even in the teacher's guide, they haven't used truth tables for this. But you know how to draw truth tables. If you need, you can apply it and get the idea. Okay, now we have completed very important things in fundamental things in logic gates. You know, basic logic gates, then combinational logic gates, and other gates such as exclusive OR and exclusive NOR. And the final term we discussed today is universal gates. Right. Then we are going to discuss Boolean laws and rules for simplification with the next unit. Okay.